So this is Project Oxalic. We have been trying to get through the nightmare that is Rust reversing, so we'll kind of walk through that and promise to give you a glimmer of hope by the end of this. It's not solved, it's not terrible, but we'll get something through. So first and foremost, my name's Juan Guerrero-Saade. Jags is fine. There's at least one person in the crowd who can say it. I'm over at SentinelOne, running the Sentinel Labs team. And this is Nicole. You want to?
I'm a security researcher at Intezer. Yeah, that's my first gun. So
there you go. All right, so this is not going to be pleasant, guys. This is going to be rough. We've been working on this for months, and it's still pretty rough. So I think for everybody in this crowd, it doesn't take a whole lot to get the point across that it used to be that we just kind of be frustrated with what was happening with Delphi and C++, and I think everybody's still kind of frustrated with C++ in general. But beyond that and some crappy edge cases, I sense like we've kind of gotten into a pretty good cadence about reversing in general, except now it seems it's just the ecosystem's being populated and sort of getting worse, right? So in a large part, I feel like we were going about things like Delphi and C++ reversing kind of wrong. I think it's kind of born from this notion that sort of badasses just stare at disassembly, right? Like you don't F5 reverse your way through this. That's not cool. You've got to know what's happening at assembly level, and that's how you really understand what's going on. I think that's wonderful if you want to feel good about yourself and like how elite you are, right until the point that you have multiple layers of abstraction involved, which is precisely the point with all the difficulties that we have with C++. And frankly, like that's what decompilers are for, right? Like that paradigm was invented not for the frills or for the fun of paying for a more expensive IDA license, but because we wanted a certain ability to abstract and then hopefully build on top of those abstractions. The same way that we've built that into programming languages, we're going to want to have it in our reversing tools. So the truth is that now we need them more than ever. And this is frankly like the biggest, one of the biggest learnings from just taking Rolf Rohl's C++ reversing course, which if any of you have a chance to, it's actually really good, but you're gonna live in the decompiler and you need to get rid of that notion that we can just sort of disassemble our way through this. So things are going from bad to worse. If any of you have been on like techie YouTube lately, I'm sure you've seen that there's a bajillion programming languages. They just kind of keep popping up. Someone's got some fantastic new notion about how we should handle like variable scope or whatever, and they create a new language. And every one of these is its own pain in the ass for reverse engineering. Most of them suck, right? Like, sorry. Most of them suck to reverse. Let's, whatever. They're massive binaries after compilation. You usually have a ton of stuff statically linked into it. You have these like arbitrary binary structures where they'll just decide how they want to link things. Unconventional or custom calling conventions, or better yet, the ability to define whatever calling convention you want at runtime. And you have these really active development communities that often turn into just factories of arbitrary changes, which is not fun for any of us because we don't have the equivalent size community to kind of hedge that off. So I think the bigger issue is that our tools kind of suck even more, right? Like I said, we don't have an equivalent community, which also means we don't have an equivalent sort of like development cycle, right? We're not going to be able to catch up at the same pace. We're not putting the same effort and scope, and the use cases are all different, but you have a very small ecosystem of folks maintaining these tools. So issues like type reconstruction and complex function prototypes, or even just think about small things, right? Like how do we handle having multiple return values? It's like a fundamental feature in Go. It's not a thing that we've ever had to model with our C pseudocode decompilers. So the problem that arises from there is that when no one is looking, when no one's paying attention to some of these languages, you get this sort of buildup of misuse. And that's something that we saw primarily with Go, right? There was a period of time where nobody wanted to reverse Go. And in that meantime, you saw APTs, ransomware, e-crime, everybody sort of adopting it and taking advantage of it, enjoying the concurrency of it. But what we also figured out in trying to tackle Go and Go reversing is that there is kind of an interesting sliver of hope. So I want to run through the notion of sort of like how we tried to solve reversing Go, and I'll do it very quickly. But just so you have an idea of kind of how we wanted to approach Rust. So why did reversing Go suck? Well, the multiple return value thing that I mentioned, but also you had these like complex types, you had difficulty with type recovery, you had this constant difficulty with user code kind of being buried in mountains of statically compiled like library code. Stripping binaries would mean you lost, it seemed like you lost a whole lot of information. The stack would get reinterpreted every time that you were trying to decompile. So then, I don't know how many of you have dealt with like the more context problem in IDA Pro, but if your decompiler ever just decides it will no longer handle any Go binaries, it's because the stack has been messed up in the function that runs before it and keeps getting reinterpreted and sort of everything breaks. So what we tried to do at the time is basically come up with this thing called AlphaGolang, and I've presented on that before, and I won't bore you guys with it, but essentially the idea was to try to tackle two disparate problems. One of them is the brittleness of stuff in IDA, IDA Pro, IDA plugins, and IDA Python in general being kind of a brittle mess, and that I'm sure is a problem everybody here is relatively familiar with. I'm about to, we're going to make it worse for you guys. Tried to make it better, but it's just going to get worse. So instead of trying to make like a monolithic plugin that was bound to break the way all of them do, we just kind of went about it by doing these like series of small scripts that you could use as subsequent steps. So worst case, one of them breaks, you can still go after the other one. If one of them is not compatible with your use case, you can sort of jump forward. So it was more of like a methodology of reversing. And that's what we wanted to do. But at the end of the day, the methodological goal is the same one that we're going to take over into our Rust project, which is we want to surface all of the structural or inferred information before the analyst gets involved at all, before the reverser really gets involved at all, if possible. There's a lot of work that ends up occurring where you're just, if I'd run this script, if I'd known about this tool, if I knew about this struct, I wouldn't have had to waste all my time on X, Y, Z. Okay, well, how about we just make sure that we try to get as much out of it surfaced to the user before they start to sort of tackle things. And in Go, it was particularly fruitful. So our methodology, real quick, we were able to identify Go binaries, just run a YAR rule, grab as many as you can, do whatever you want there. We can recreate the PCLN tab, which is really interesting because for those of you that were dealing with stripped Go binaries, all that was happening is they're essentially removing some of the flags around this PCLN tab section, but they don't remove it. If you remove the PCLN tab section, the whole binary breaks. So stripping in Go is really not that bad. It's just not letting you know where the information is, but the information remains within the binary, which is amazing. So you can just recreate it with some simple heuristics, which then meant that we could rediscover every missing function inside of the binary and also restore the function names from the original. That's why sort of these garbling obfuscators are so popular in Go. You can't actually remove this information or you'll break the binary, so let's just rename them some like arbitrary name. Then from there, it's really easy to surface the user-generated code. We could fix the string references because the strings get loaded as sort of like a slightly different way, right? Pointer to a place and then length, so it's safe, but Go, IDA doesn't know what to do with that, which is why you get these like giant blocks of strings. They're just not null terminated. And then you could extract type information, which Justice Rage, I don't know Ivan if he's here, but he contributed to it. So we could actually get back a fair amount of type info, sort of put it right back in. So by the end of it, one example we got is when Desert Blade came out during the Ukraine conflict, Go binary, pop it in there, 2,400 functions in need of reversing, run through the 5 scripts, and we ended up with 8 user-generated functions. Done. Beautiful. I actually prefer to reverse Golang these days than anything else. It's actually really easy. Okay, cool. So past accomplishments, wonderful. But what about Rust? Because what ended up happening when we finished with Alpha Golang is this notion that we realized just how bad that malware ecosystem was and is and continues to be. So what's happening with Rust right now that, I don't know about if there's any sociopaths in the crowd, but like, I'm pretty certain most people are just, they see Rust and they move on. Anybody here fond of reversing Rust? No lies detected, but.
This one?
Yeah.
So Rust. So Rust has been around for a while. The first stable version was released in 2015, and the first malware was detected in 2016. But what is so special about Rust? So it's cross-compiled, which is nice. It's memory safety oriented, a very strict compiler that would detect lots of like memory and other like possible vulnerabilities during the compilation. No garbage collector, supposed to be faster than C, has a very strong and capable manager called Cargo. And basically we have multiple versions of Rust, the stable versions, and also a new nightly version that is released every day. So you can see how it can be hard to like see what's going on there. And Rust becoming very popular language for malware. We see it both in APTs and in ransomware. So for example, Wildcard, it's an APT that was targeting Israel. It was rewritten from C to Rust. More examples are Luna or Hive, which is a ransomware that was rewritten actually from Go to Rust. So we can see a shift towards using Rust. But why? First, because it's painful to reverse engineer. It produces huge binaries, lots of functions, lots of strings, but usually the interesting strings are obfuscated or encrypted. The functions are very long, multiple stack variables, and it's honestly very painful to do anything with it. So why are we so reluctant about reversing Rust? Why like no one is reversing Rust in this room, right? Because it's hard, because it's painful, because we're not talking here about NIM or Zig or Kotlin or whatever. It is hard and we don't want to deal with it. So is there hope? No. Okay, maybe there is a bit of hope. Tiny bit. So we started this project with, let's do something similar to what we did with Go, right? Step by step, see what we deal with, open some binaries, maybe compile some Rust binaries, understand that it's very hard to compile Rust because of the compiler. We wanted to quit several times from this project, but then we got accepted to the conferences. Had to do it. We chose some like malware binaries, for example, the Wildcard or Black Cat, just to see how malware actually looks like. We wanted to find maybe patterns or something that we can recreate, something that we can extract and use, similar to what we did with Go. And in the process, we were very frustrated because of IDA-Python and IDA and so on. And you will hear about it more. So the first step was identify Rust binaries, which is relatively easy because of the strings that are left by the compiler. And then we wanted to see, okay, what information we can actually extract, just as running strings or something on the malware samples. So we actually find lots of strings, and some of them are the Rust C version, which is leftovers from the compiler. So we can know exactly which version of Rust was used, because the string that you see is actually the commit ID from GitHub. So that helps, I guess. Then we have a bunch of strings from the cargo, from the dependency manager. So with that, we can know exactly which libraries and versions were used in this specific sample. Keep that in mind. And then the next step is strings. So Rust has this amazing thing of strings and slices and mutable, immutable, lots of fun. But under the hood, strings are just some sort of a structure with the capacity, the content, and the actual length of the string. And slice has only the length and the content of the string. And this is how it looks in the memory. So we created these structures for IDA, so we can parse these strings and hopefully make the analysis and the decompilation nicer. So this is how the strings look, both for 64 and 32-bit. So if we will take a very simple Rust code that defines a slice, what we see is basically that the code has the slice and some length, and in the decompilation it looks weird, and the content of the slice is in the R data section. However, there are some slices that live only in the R data section, and part of these slices are actually some paths to these car codependencies that we saw from the output in the slide before. If we go a step further into immutable strings and other sort of creatures in Rust, it becomes much worse. And mind you, this is like a simple sort of hello world, and you can see how 2 lines become this mess. And then what if we want to create a string and then append to it a string that is longer than 16 characters? At first, we can see another way to basically move strings in the decompilation, and then we're getting XMM words and a bunch of other strings that are reversed. By the way, reverse strings in XMM words, it's not only for Rust, it's a thing in IDA. In the binary, it looks the same, it looks right, but here is another. For the first 16 bytes. Yes. So that's another thing that needs to be fixed. So once we were able to clean up, we defined our structures, a bit of manual labor, a bit of Python, and we were able to basically get a nice decompilation, but it was painful. And again, that's like hello world. So right now, the issues with slices is that the content of the slice is in another section, and we need to bring it. We need to learn how to parse it and how to actually apply structures in IDA, which is very painful, not straightforward, and very painful. Calling conventions in Rust. Basically, there are, but there are none, because it supports all the calling conventions. So who knows? That's fun. So we decided to maybe use some of the unwind metadata. Basically, when when a program crashes in runtime, the runtime needs to know how to basically fold it and how to handle the exceptions. So for each function, there is a structure called unwind. And it has a bunch of information about the registries that were used and the frame registries and the size of the stack and so on. So this structure has a very documented structure that actually at first at IDA wasn't parsed correctly. So we reached out and they helped us and basically fixed it. So now when we parse that, for each function we can know the flags, the size of the prologue, the non-volatile registers that are being used, and so on. So our hope was that we can use this information to maybe be more certain about the calling convention that was used in this sample. But unfortunately, that's not enough, because we need also to know the type information. So that's something that we're still working on. And for the future work is actually to try other formats like macOS and Linux, because they have different calling conventions, and maybe we can get something more useful from there.
Yeah. Not only do they have different calling conventions, the way they do stack unwinding is completely different, so it's a wonderful time. That said, there's also some wonderful bits in Rust in that because it's such a macro-driven language, it actually does a whole lot of things without the developers necessarily knowing or thinking about it. So like even when you're doing like a print or some other sort of like very basic operations, expanding out that macro actually involves a whole lot of like safety checks, which means a lot of information that's sort of making it to the binary that the attackers might not know is actually there. So when you're looking at, look, this is kind of the usual mess that you run into and millions of pieces of this throughout a Rust binary. But if you notice, there's this sort of offset at the end of that function. And looking at that, it sort of showed us, oh, look, there's another random struct that's being sort of shoved into the middle of this. So trying to pay attention to the information that's there, we came into something really interesting. So we created this structure, we defined a structure called debug info, and when you start to apply it, you start to see something really nice. It turns out that in order to know how to handle a panic, this macro expansion will actually tell you the source file, including, remember, the commit ID, the line and column number of where this panic would have been triggered. And that's all just kind of hiding right under the hood. So the minute you do properly structure this, you can actually start to find line references within how some of this code is being pushed. And keep in mind the commit ID thing, because we'll kind of go into it in a little bit. So then what you could do is sort of go through the entire binary and start to sort of resurface this information, and then sort of restructure how all of that is put. Then you can move up the stack and start to identify all of the structured exception handling. So you go, okay, well, I know what these line numbers are. I know where they're being called. It turns out they have their own sort of structured exception handling functions. You rise up, start to define some of those structures. And a lot of this information just starts to kind of fall right into place in some nice ways. Again, slivers of hope, right? 2,400 functions, 24,000 functions, and you go, oh, it's wonderful that I was able to identify these 50. You go, great. That said, there's another obsession that we're on now, which is this notion of, how familiar are folks with birefs, like biref variables? So essentially, you can have references within the stack that are done by reference to a specific offset in that stack, and that can actually violate scope in some ways. And that's been really interesting, because something we noticed as we were looking at all these functions is a lot of them have a lot of references to these stack variables by reference. And it started to make us wonder if Rust has a special way of handling scope across functions that are all sort of being called in a certain execution flow. Folks smarter than I in the crowd at Recon mentioned that it might be this notion of closures that is being sort of taken advantage of. But essentially, the reason I'm so obsessed with it is if we want to understand how data is being altered inside of a program, and we don't know where the variables are being referenced from within these other relevant functions because they're violating scope in the stack, we're screwed. And that's kind of what it looks like when you're trying to reverse it. You go, where the hell did this variable get changed? IDA goes, never seen it being used anywhere else. It turns out that there are these sort of manipulations across the stack in ways that I think would not be allowed, quote unquote, in other programming languages. I do hold on to the possibility that these are ghosts in the machine based on how bad the decompilation currently is. There's a lot of like dead variable storage and stuff. And then also like the amount of type miscasting. Maybe if we clean all that up, all these birefs go away. But there's too many of them for me to really kind of push it all out completely. So we've been working with IDA, with the guys at Hexrace to try to fix some of this, and we'll get into some of that in a bit. So when we put this slide in originally, we thought Ilfak was our only hope, and in some ways he is, but he was in the crowd when we talked about it the first time, and he was kind enough to kind of offer a lot of help and sort of jump right in. But then we realized that that really wasn't going to sort all of this out for us. To be fair, Ilfak's been great, Hexrace has been great. They've been really trying. They have a lot of other stuff going on. As you might see, IDA Pro 9 RC1 is in beta right now. And that's sort of leading to where a lot of our like current work is. So I'll go back into the IDA9 thing in a bit, but do you want to take any of it, or yeah? Out. All right, so what are we working on now? Well, first of all, we mentioned all those cargo dependencies, commit IDs, and so on. If you look at it, there's a sort of really interesting ability to just be able to at least list out the dependencies, interdependencies, and with specific versions and commits, which is a really nice bit of specificity, and it's something that we should be able to take advantage of, right? You can kind of parse that out, and great, you have the string, who cares, right? We want to fold that back into IDA Pro somehow. So it turns out that, we can, based on that, essentially go, this was the specific version, a specific time commit for this dependency. Pull it down, compile, turn it into a flirt signature, and then apply it. And we've been trying to automate some of that. Other folks have already automated some of it. Some folks at Hexrace have automated some of it, and none of it is available to you at this time. It's a mess. But it does make like a really big difference, right? It's a big advantage when it comes to all this heavy lifting that you have to do for all these dependencies that you can't tell. So I think the solution to the dependency problem is within reach. Is it a satisfying one? Not yet. But essentially the way you have to look at it is we've been kind of stalling with IDA9 coming out because basically we need the better ability to sigmake within IDA and to be able to determine which signatures to apply when, and then to be able to sort of pull this stuff in, and it becomes kind of clunky. But pipelines are being created for it. So any of you in the beta for IDA9? We got 2 folks. Awesome. Sorry. It's rough. So one new thing that's being added that we're pretty excited about is this Flirt Signature Manager. I tried to record a demo very quickly today, but essentially now you can get all these Flirt signatures in there and actually have it sort of test out what applies, and it will tell you this is the best signature that should apply here. It has 58 matches or whatever. Click, and then all of a sudden, 400 functions are now well labeled. Awesome. Great work, Hexrace. Now the problem is this is all for the standard Rust part of it. It's none of the dependencies bits. So now what we want to make is more of a pipeline to handle it and process that for folks. I don't know, how much time do we have left? Anyone in the back?
It's about 5 minutes.
5? All right, that should be good. Okay, cool. So where does that put us for now? This is our methodology as it stands right now. It's just what we've been showing you, and we have scripts for all of these. As of today, tomorrow, all these scripts are broken because IDA9 changes all of IDA once again. You're going to love it. It's going to be great. So in the meantime, we kind of went about creating this ancillary tool that I called feature proof. And the idea was to create sort of this middleware library that would simplify some of the functionality that you would want for your IDA Python scripts, and then we could re-implement under the hood based on what version, and then hopefully we can have scripts that don't break every 6 months. I know, we dream. I'm still working on trying to port the underlying bits to IDA9, but I can use the help, and maybe it'll help you make some scripts a little easier. There are still things that we can't seem to fix, right? Like we really wanted to try to get structure creator from like C syntax files. Not working just yet. I think I went through 49 iterations, me and ChatGPT. We'll try to fix it. Maybe now with idalib. So where do we go from here? Well, as Nicole mentioned, right, Mako and ELF have entirely different ways of handling stack unwinding that we think are going to have a lot more information. The reason we're so obsessed with the stack unwinding is that's a great way for us to figure out some of the calling convention stuff. You can double check whether the decompiler is actually giving us a good stack when you know authoritatively that the stack is supposed to be this size. It's supposed to have these registers being used in this and that way. So we're going to keep going down that path. There's also, if we can sort of recover some of that calling convention stuff, I think it'll make a big difference. But at the end of the day, the decompilers are broken right now. Like, just straight up. Ghidra, Binja, and IDA Pro do not have specific handling for Rust. The Vector 35 guys might throw a brick at me because they're so fast. Like I think they've already kind of gone through improving it. But I can at least say like IDA Pro, there's a hope. They know it's a project, they need to take it on, but the decompiler itself is just not made to handle it. So what you'll see is like tons of ghost variables and like all this stuff in there that we showed you a cleaned up version of a function. It starts cleaning up and you go, okay, this is great. If you just apply some structures, it all starts to look cohesive. And then you keep going and then all of a sudden it all just unravels because it starts reusing variables and things that you just know are like decompiler errors and not actually part of this. So some of it we're just waiting. We're gonna have to wait until they fix the decompiler, but I'm hoping that sort of like the broader set of this problem we can sort of fix with external information. So we've expanded the project. We said we'd do it for 6 months. I think the hubris of that was mostly mine, but kind of fascinating. So we're gonna keep going with it. The eventual goal is to enable us to hunt sort of through the deeper malware ecosystem and come back maybe next year and say, look at all the stuff that was lurking there. But in order to do that, we need to be able to analyze some of this stuff. The more likely outcome is that we'll just decide to become farmers. So have we learned anything that's valuable for hunting? No, maybe. What we are going to be working on for the next 3 months as we improve some of this pipeline stuff is rather than trying to just create a signature for everything that has ever existed, which makes no sense, we're sort of doing a bit of like a big data survey of everything that's been compiled in the wild from Rust and say, okay, these are the dependencies that are most needed, most common, and I'm kind of hoping we'll just build flirt signatures for everybody and host them on GitHub somewhere and just be like, fuck it. But the Hexrace guys might get ahead of us and actually build a pipeline for that for you. We'll see who gets there first. We just are not gonna wait. Shout out to VT and Mike Holmes and some of these guys that have been helping us with sort of the general amount of samples. As you know, RC1 is out. There's a lot of exciting features. It's not gonna fix your Rust life, but what we will do, and I'm committed to this, is I will make the repo for Oxalic public today. I'm committed to it. Throw a brick at me if you see me at drinks and it's not done. And with that, I don't think we're gonna have time for questions, but we'll be around for the rest of the conference, and please come talk to us. This is like a major problem we need a lot of help with, but I hope it kind of gives you a bit of hope and familiarity. So thank you, guys.
Okay, thank you.